Hello, my name is Amashni. In this lesson, we will be looking at a geometrical property called similarity and how it specifically applies to triangles. Here is what we would like to achieve in today's lesson. By the end of this lesson, you should be able to explain the term similarity. You should already know that when figures are the same shape and the same size, they are called congruent figures. We can use transformations to show that these figures are congruent. Can you remember what they are? We could flip one figure onto another. We could slide one figure onto another. Or we can rotate one figure onto another. So we see these two figures are congruent, these two figures are congruent, and these two are also congruent. Now, when figures are the same shape but not necessarily the same size, they are called similar figures. Take a careful look at this artwork. Do you see any similar shapes? Well, if you look at these triangles, they do look similar, don't they? But although they are not the same size, they do look as if they are the same shape. We can identify similar figures in two ways. We could either shrink the figure until it is the same size as the original, or we can dilate or inflate a figure until it is the same size as the original. The word dilate means to expand or to make bigger. A very good practical example of the same figure being made bigger or smaller is maps. Here we have two maps showing the position of South Africa. In this map, South Africa is shown in relation to the rest of Africa. In this map, South Africa is shown in relation to the rest of the world. In both cases, the same figure or shape is represented, but in both cases, map makers had to use some sort of scale to ensure that the figure represents South Africa in a realistic way that corresponds to its actual size on the globe. The construction of similar figures can also be called scaling. Most maps provide a scale that helps us to calculate the actual size of a region that is being shown. Depending on the size of the map, 1 centimeter on the map might represent 1 kilometer in reality. In this case, where a large region is being shown, 1 centimeter may represent 100 kilometers. We can say that our map has a scale factor of 1 centimeter to 100 kilometers. So let's take a closer look at how we determine what the ratio between two shapes is. For this activity, we will use a computer program to help us. Here we have a square. The length of the sides of the square is 6 centimeters. I have entered information in the dialog box which will halve my square. Let's have a look at the results. Do you see that we have a new reduced square? A prime, B prime, C prime, D prime. The sides of the figure are half of the lengths of the sides of the original square. Remember, when we have a scaled figure, we must only look at the relevant information. In the case of our square, we needed to look at the lengths of the sides only. But in this series of lessons, we are dealing with triangles. So if we say that similar triangles have the same shape but a different size, do you think the lengths of these sides of the similar triangles influence the size of their angles? Again, we will use a computer program to construct similar triangles according to the following ratios: 1 to 2, 1 to 4, 1 to 8, and 2 to 1. This time I have made a printout of the results, but before we look at them, think about the triangles you expect to see. The ratios we will use can also be represented as 1 divided by 2, 1 divided by 4, 1 divided by 8, 2 divided by 1. Keeping this in mind, do you think that the new triangle scaled in the first ratio will be larger or smaller than the original? What about the ratio 2 to 1? Let's have a look at the triangles we printed out and see if you had guessed the correct sizes. Do you see that when the ratio is less than 1, the new triangle, also called the image, is smaller than the original? When the ratio is larger than 1, the new figure is larger than the original. For the rest of this activity, we will focus on these two triangles. the original and the triangle that has been scaled in the ratio 1 to 2. That is, the triangle that is half the size of our original triangle. Do you remember I asked you earlier whether the lengths of the sides of similar triangles influence the size of their angles? Let's measure these angles in both these triangles and find an answer to our question. Let's measure the sides and angles in both our triangles and then write down our results. Now we'll take our protractor and measure the angles. We'll start off with angle G. So we see that the sides are also in proportion to one another. In this triangle we have 8. Here it is 4. In this triangle it is 7. In this one 3,5. Here 12,5 becomes 6,25. So we see this triangle is half the size of this triangle, or they are in the ratio 1 to 2. If we look at the angles on the other hand, the angles are the same. 30 degrees, 30 degrees, 35 and 35. So we see that our two shapes that are in proportion have the same angles, but the lengths are halved. Now we know that in the scalene triangle, the sizes of the corresponding angles in the original as well as the image are equal. Do you think this applies to all triangles? I have constructed two similar isosceles triangles in the ratio 1:2, as well as two similar equilateral triangles in the ratio 1:2. Let's have a look at the measurements of these angles and sides. We start by looking at similar isosceles triangles. Let's find the lengths of these sides. ZD is 13 centimeters. ZR is 13 centimeters. The length of DR is 17,5. Let's now measure the image. Let's use our protractor and measure the angles in both these triangles. We'll start off with angles at Z. Let's now measure the angles in the image. At angle R prime, we also get 47 degrees. Angle Z prime is equal to 86 degrees. And at angle D prime, we get 47 degrees. Do you still remember what makes these triangles isosceles? In isosceles triangles, we have two sides that are equal in length. Remember, in the isosceles triangle, we also have two angles that are equal in size. In an equilateral triangle, all the sides must be equal. In our example, all the sides are 14 centimeters in length. The angles are all 60 degrees. Now, do you remember why that is? Yes, the interior angles of a triangle add up to 180 degrees. Can you see that in both these triangles we have the same results as with the scalene triangle? Although the lengths of the sides differ, the sizes of the corresponding angles remain the same or equal. Do you think that now, after these observations, we can define this geometrical property of similarity in triangles a little more clearly? Similar triangles are the same shape, but they are not necessarily the same size. Two triangles are similar when all corresponding angles are equal and all sides are increased or decreased in the same ratio. Thank you for joining me in today's lesson. Be sure not to miss our next lesson where we discover how to apply rules of similarity to everyday problems.